Hello, everybody. This is Tim Lankish from CAE Services. We're going to wait just a few minutes here before we get started to give everybody a chance to jump online here. So sit back and relax, and we'll be starting soon. Hello again, everybody. If you're just joining, we're going to wait a few minutes to allow a few of the latecomers to jump online here. So we'll be starting in a minute or two. Okay, well, welcome everybody. Thank you for taking time out of your day to join us. My name is Tim Lankish. I'm the Director of Engineering at CAE Services, and the topic for our webinar today is understanding GM's Moldflow requirements. I also have Darren May, who is an engineering group manager for GM. Darren was very instrumental in putting together GM's requirements. So he'll be available at the end of this session to help answer any questions that I'm not able to answer. So welcome, Darren, and welcome everybody. So let's get started. So a little bit about me. This is my background. I've been around a long time, 27 years at CAE Services. I am expert certified in Moldflow. I've trained many expert certified engineers. Presented at the Moldflow Summit. I've written some articles for some trade magazines, so you may have seen me around a little bit. And a little bit about CAE Services. We've been around since 1988. We have the most expert certified Moldflow engineers in the world. More recently, we've become an Autodesk partner, and we've completed some 24,000 plus projects over the years. So got some good background in Moldflow, and we have the technology center, as you can see there. with molding machines. So all of our guys are trained to be able to run a machine, and it's always good to be able to put mold flow simulation results into practice. So that's a little bit about us. So we're going to be talking about GM requirements, and I'd be curious to know, what your initial reaction was when you heard that you had to be compliant with GM standards. And if it was anything like my initial reaction, it maybe wasn't entirely positive. Like, what, you don't trust us? You don't think we're going to do the right thing? But over time, I've realized that this is really a good thing that GM is doing. So your reaction may fall into one of these categories, like, "Oh, brother, why do we have to do this? What's the point?" Or, "Yeah, I'll do it, but they won't pay attention. It'll fade away." Or, "I'll do it, but I'll do it my way." And I've seen that happen out there with some suppliers, kind of going off the reservation there, so to speak, to do it their own way. Maybe you feel like you don't have the time, but I would argue that uh, spending the time to do this actually saves you time in the long run. Or maybe you're just of the opinion that Moldflow stinks. So, and there's an awful lot of that opinion out there. But here to tell you that if you do things right, there's really quite a lot of benefit to using standards. And here's some examples that Darren provided for me. And this is actually one we worked on ourselves. You use the design for example, in this case, a conformal cooling. You simulate it and you manufacture it and you test it. And in this case, we were able to improve the mold temperatures by 30%. But not only that, when we compare to the original design using standard cooling, conventional cooling, you see how not only did the part temperatures change and we got more uniform cooling, but you look at the change in warpage and how it changed this angle over here in the part. And beforehand, if you measure the warpage at the tip here, it was 14.6 millimeters, and afterwards it was 9.4 millimeters. So there's a lot of benefits to doing things the right way in Moldflow, and it shows up in the manufacturing of the part as well. But on the other hand, there's consequences of ignoring standards, and these are just a couple of examples. So uh, with this liftgate trim, Moldflow was predicting large warpage and no action was taken. And you see how this showed up in the gap and flush issues here. And when these types of things happen, it costs a lot of money to fix them. So um, you see all the costs and the number of days that added up to trying to reduce the warpage in this part. So standards matter in terms of part quality, but also timing and money as well. Here's another example where uh, the warpage wasn't paid attention to, and they ended up having to do a couple of windage iterations, cost them $64,000 and 40 plus days of doing a a trial and error type of windage analysis. So you see the original tool was cut down here. They did one windage attempt that didn't quite get it. They put a little bit more windage in there and finally got it. So these are the kinds of things that GM over the years has noticed and taken the time to try to fix ahead of time, being proactive about it using Moldflow analysis. Here's a more recent example. Now, this is not an automotive part, but this is a part for the ventilator project that GM was engaged in. The point here is windage is becoming very common, and we've worked out a methodology to be able to do this very rapidly. We were able to turn this around in 1 week's time to be able to bias the tool using Moldflow analysis as our guide, then morphing the part and doing some windage checks to be able to get the final part where we want it. So you look at the animation of this, the main problem was perpendicularity of this part. And we were able to correct the out of tolerance issues with the perpendicularity of this L shape and also this boss up top using several methods, moving gates, changing the part design of this tower, and using windage. So several things went into that, and we did it inside a week. So very rapid response for that. And then appearance issues as well. You see the sink marks on the left here that were corrected partially by moving the gate here and also improving some of the processing. So those are the types of things that can be achieved if you use standards. And these are the documents that are involved in the GM standards. It all stems from the Appendix E8, if you're familiar with that. It's a manufacturing statement of requirements. The two we're going to focus on are the GMW 16355, which relates to the injection molding analysis, mold flow analysis, and then the 16365, which is the T1 tryout protocol. These are available for download on IHS website at ihs.com. So if you don't have those standards, I recommend you go to the website and get those, and then you can read them for yourselves. This particular webinar is intended as kind of an overview to help you understand what's involved, but those documents will give you, the nitty-gritty detail. And then ultimately, this is intended to enable Kaizen improvements, meaning, you want to be improving over time with the realization that, things may not be perfect as you start, but over time, as you learn more and more, you improve upon the standards as time goes on. And that's exactly what GM has done. These are what these standards look like. So on the left, we have the 355 standard, on the right, the 365 standard. So it's a lot of reading, but there's good stuff in there, and it's very well done. So why did GM do this? So they took a survey of the automotive industry, and they found that there was a lack of Moldflow standardization. People were using Moldflow as a checkbox or a pretty color chart to satisfy customers, getting wildly different results on a lot of different things, and there was limited support for those Moldflow results or confidence in Moldflow results. You may have one guy that's an expert doing the analysis, and you may have another guy that was told, "Hey, you're the Moldflow guy. You guys got to provide a Moldflow, so get at it." So you never knew what you were going to get, whether it was good or bad, and consequently, you end up in those situations where you get some bad Moldflow analysis, and it turns into a lot of rework, a lot of money spent, and a lot of time spent. And this is kind of a chart that helps explain that. So if you do upfront analysis, the amount of effort and work is less, and things just go better overall, rather than getting into these situations where you're doing firefighting analysis when you're ready to cut steel on a mold. So GM studied Autodesk Moldflow very carefully, and found that it really should be used for more than just gate locations, and that's oftentimes what it was being used for. But if you're expert certified and you spend a lot of time in Moldflow, you know that Moldflow can be used in a really powerful way. It's great for both part and mold design development. And then, as we mentioned on the previous slide, we're using Kaizen to improve the entire Moldflow user community. So the standardization helps everybody get better over time and helps the results be more uniform over time. So overall, by doing this, GM has experienced better results through standardization and correlation. And ultimately, when you expect better, you get better. Low expectations give you poor results. If you have higher expectations, ultimately, you can expect over time things to get better, not just with the users, but also with the software. So it's also used to push the software developers to improve things. So here's the 355 in a nutshell, and this pertains to the simulation end of things. So it's a course-defined Moldflow to influence part design. So it starts off early on, more in the course type of analysis, getting a 30,000-foot view of what you're up against when the part designs first come out. Now, there are three distinct events, and we'll explain these in a minute, but MF0, MF1, and MF2. And there are 5 phases of Moldflow that are interrelated with that that we'll explain as well. It's a consistent and comprehensive structure in their standard. So, for example, we'll talk about resin characterization guidelines. We'll talk about what is expected of the analyst. We'll talk about the GM internal approval process for the Moldflow analysts, and we'll show some of the explicit outputs at each phase. So GM's global vehicle development process has certain milestones that align with Moldflow, and that's what these charts explain. And I'll kind of highlight some things here. So we have MF0, which really isn't included in the GMW 16355 standard, but this is done at the Seaver stage, as you can see here. And this is the 30,000 foot view Moldflow. During this phase, you're looking at filling, packing, and warp analysis. Obviously, we're way ahead of mold construction here, so you won't have a cooling design to really look at. But it's taking a look at whether or not this part is manufacturable, in the early design stages. And to GM's credit here, a lot of the Moldflow we used to do going way back when, we weren't engaged typically until the mold was ready to be built. And unfortunately, at that stage, it's really too late to incorporate any design changes that might help warpage, for example, or help a filling pattern change to get a better knit line. Because it always had to go up the chain to get 100 signatures to make a design change, and meanwhile the mold maker is waiting to start cutting steel. So that's not the best use of Moldflow analysis. Really, the best use is well ahead in the design stage, so that you can affect part design to the extent that it improves the things you want to improve. So that's really the main idea here. Not every problem that shows up in injection molding can be fixed by processing or by mold design. And I'm sure a lot of you have experienced that. A lot of it really boils down to the part design. So if you can get to the point where you're affecting the part design early on with Moldflow, that's the place you should begin. And that's where MF0 is, at the Seaver stage. Then we move on to the MF1 stage. Now we're in the SVER stage. And now we're adhering to the 16355 standards. We're doing fill, pack, and warp analysis. Things are a little bit more developed here. You're developing, runners and gates and filling patterns are the things you're establishing here. It's Moldflow phases 1 and 2, which we'll talk about in a minute. And then the last stage is where now you're into mold construction, and you've got cooling designs available. You've got full-blown manifold, runner and gate designs, and so forth. And that's at the IVER stage. So those are the 3 basic stages of Moldflow, and there's some other intricate details here that we could talk about, but that's more for an in-depth class. So what's in the standard itself? We'll start with material characterization. And this is one of the biggest things I think that is very important to pay attention to. And this applies to any type of simulation. It's really garbage in, garbage out. I've preached time and again about these things over the years in webinars and trade magazine articles and in training. You cannot expect good Moldflow results if you're not putting good data into it. And there are some 11 data sets that go into a fully characterized material for injection molding. Okay, so and Moldflow has a database of some 11,000 materials now. Not all of them are fully characterized for those 11 data sets. And sometimes if they are, it might be old data. It might be something from back in 20 years ago or more. So GM took it upon themselves to include this in the standards, that no UDB file older than 3 years could be used unless it's been verified. And in fact, they even went to the extent of building their own database of materials and funding that. So you can look in the Moldflow database if you have Moldflow and look at the quality indicators, and they all should be reading as gold, meaning that it's the best type of data. It's for each of the types of analysis: filling, packing, and cooling, and warpage rather. So so having good material data really goes a long way towards getting the best results. And here's some of the consequences of not having that. Here are two very similar setups here. Everything's set up the same, but the only difference is the material file. On the left, if you don't have something called juncture loss data, you might think that you're going to be able to mold this part with just over 10,000 PSI. But with the juncture loss data, it's predicting 23,000 PSI. So this is the real deal. Sorry, this is the real deal over on the right here. If someone was doing Moldflow analysis and they got to the press and they didn't have that juncture loss data, there's a very good chance they wouldn't be able to mold that part, because now we're running up against the machine's limits. So that's one example. Another example is something called CRIMS shrinkage data. And this was an actual thing we worked on, where they ended up having to scrap the cavity side of the mold because the manifold had to be redesigned. And this is just in the beginning stages of mold or GM doing their requirements, but the supplier on this, the part supplier on this, insisted that we do Moldflow analysis despite our objections to doing it because we didn't have proper material data. And on the right here, it was predicting some 3 millimeters of warp. And after they started molding parts, they noticed that the warpage was actually much higher than that. So by that time, GM had started their materials database, and that material became available, and we reran it, and it actually predicts 6 millimeters, which was more in line with what they were seeing at the press. So the cavity half of the mold was scrapped, new manifold built. We ended up having three gate locations, and we're able to flatten that part out. So, but at the cost of time and money. So it's really important to have good material data across the board for any analysis, and everybody should be insisting on that. So not only is there a private material database for GM and the expert certified analysts that are approved by GM, but there's also a private machine database so that whenever you go to a tryout, a T1 tryout, the specs of those machines are available and can be used to benefit the analyst. So what is an approved Moldflow analyst? Here's a flow chart. We won't go through the whole thing, but we'll hit some highlights here. You have to have experience as a CAE analyst. You can't just be a guy that was thrown into doing Moldflow analysis. You really should have some CAE background. You have to go through an approval by GM, by the GM Manufacturing Polymer Engineering Group. Part of that is Autodesk certification. There are 3 levels, so you have to progress through those levels: associate, professional, and expert. You will submit an application to GM to get their approval, and you'll demonstrate the ability to identify appearance and dimensional issues in Moldflow, determine cause of those things, cause of warpage, etc. You'll have to demonstrate the ability to correlate predicted to actual, and you'll have to demonstrate the ability to solve issues, whether it's through tool or process or material or part design. So it's a process, but it's a good one. And like I said, I've trained guys up to the expert level, many guys up to the expert level, and once you get to that point, you'll really know your stuff in terms of being able to solve injection molding issues. Part of the procedure that's outlined in the standard involves mesh. There's a lot of different opinions out there on what's the best type of mesh and what should be used in what situations. So all of those things are covered in the standard. Whether you're using mid-plane, dual domain, or 3D meshes. It'll talk about runner and gate geometry, how to model for knit lines, how to model for cooling. Here's an example of poor meshing. So you can see this knit line showing on this chrome part, lighting part. And when it wasn't meshed very tightly, that knit line did not show up. However, when it was meshed properly, 3.3 million elements, that knit line shows up. So, and this is, part of the analyst approval process as well. You have to know what's a good mesh, what's a poor mesh, and how to get the most out of it so that you're not running simulations that take 5 days. So, so mesh is a very important part of it. This next part is extremely important as well, and I've preached this for many years also. Moldflow analysis really can be done kind of in a vacuum, and if you don't talk to people that are involved in this particular project, talk to other people, then you can go down a path that might be completely different than what was intended. So you want to involve all stakeholders. You want to involve the GM product design engineer, the MPE engineer, the part supplier, the tooling source, material supplier, the hot runner, Moldflow source. All of these people are going to have opinions on how to solve a particular project, so or problem rather. So for example, if I'm the Moldflow analyst and I didn't ask the question, where can I have gates? What are the A surfaces on this part? Where can I have knit lines? Where can I not have knit lines? If I didn't ask those questions, that might send me down a path of putting gates in locations that are great for processing, but poor for knit lines. Or if I didn't know what the tolerances are on this part, again, I might go down a certain path with cooling or gate locations and have a completely different idea of what the design engineer intended, for example. And then you add the tooling source into this. Say, okay, well, I have some ideas on how we can manage this, but the mold maker might say, well, we can't gate there, or we have a slide there, or we have whatever it may be. So getting input from all these different sources sets the Moldflow engineer down a path that's much more efficient than it would have been without their input. And here's just a RASI chart to show who's responsible for what, but wanted to point these two out here. So for the Moldflow analysis, you see the mold filling analyst is responsible, but having input, the tool shop's going to support it. The GM product engineer is going to be informed. The manufacturing engineers from the polymers group is going to support the task as well. The tier one is going to have approval for the final setup on this. And then when we talk about the T1 tryout process, the mold filling analyst is going to support that. The tool shop's going to be responsible. Tier one is going to be have the approval or authority over the task, and the GM is going to support and be informed about it. So in order to go down this path, and when you're involving everybody, it's good to have a discussion and ask a lot of questions, as I said. And you can use these task instruction sheets that GM provides for various things. But the first thing is the Moldflow requirement checklist, and this is just a fraction of what's actually included in here. But some of the highlights are to help you establish pertinent information, machines and so forth, materials, tooling, analysis type, what type of mesh are we going to use, what's a basic process that we might run. But more importantly, probably is to establish objectives, appearance issues, tolerances, and to propose some initial gating, and maybe even talk about cooling at this point too. maybe a cycle time target. You know, the tier ones are basing their piece part costs on a cycle that they're estimating, probably from experience. So it's good to know what that number is, so that we can gear our cooling toward that. So along with those 3 phases, MF0, MF1, and MF2, we have the 5 phases. So phase 1 is involved in MF1 and MF2. It's to establish the optimum number of gates and gate locations. Phase 2, also MF1 and MF2. The goal there is to establish a material delivery system layout and design. Phase 3 is just part of MF2, to establish the cooling channel layout and design. Phase 4 is to establish optimum process for dimensional stability and acceptable appearance. So now we're getting into the actual tryouts. And then phase 5 is reconciliation and validation of Moldflow results to the processing data that was acquired at the tryouts. So phase 1, in the standard, this is all listed in the standard. These are the minimum outputs, and it just lists them straight down the line here. And we don't need to read it all, but look at those and you'll see that most of this involves filling, packing, and some basic warpage dimensions, or deflections rather. Minimum outputs for phase 2, adding a few things. So it's everything that was in phase 1 plus this. Same with phase 3. Now we're adding more cooling type results. Phase 4, now we're getting into a lot more dimensional type results. We're also looking at a DOE simulation here to identify the top 2 variables that have influence on the results. And then lastly, reconciliation and validation of the Moldflow results in phase 5. So dimensional roadmap showing the analysis versus the actual correlation, and an appearance roadmap showing analysis versus actual. So for this, you can also use the TIS 3.1 document as a guide. This is the Moldflow analysis checklist. And what it does here is it shows you the pertinent outputs, gives you guidelines for the results for filling, packing, cooling, and part deflection or warpage, and then also for process. It also gives you some comments over here on the right to help guide you as to what you should look for. So this is, and one thing I should mention is that there's not a standard template, if you will, from GM that you can just fill in the blanks. Typically, the suppliers are developing their own template. We're no exception to that. But we're often doing preliminary reports. We're reporting out gate locations. In this example on the right here, we're showing flow leaders and restrictors to affect the part design that need to be implemented back into the math data. But with the final reports, we're also putting in the TIS 3.1 specific items on a page-by-page basis. So at the end of this, I'll go through a quick report just to kind of show you what's involved in that. So that's the Moldflow standards. Now we're going to move on to the T1 tryout standards, and you know, there's 5 different stages there of the tryouts, T0 through T4. The T1 tryout, the purpose of that is to get parts off the tool at the tool shop, and the output is surface and physical and dimensional issues that need to be worked out. So basically, this is the one we're going to focus on here. It's a correlation process at the T1 tryout. The goal is to produce an acceptable part for a matching submission. And this is one comment Darren made to me, which I thought was a good one. GM buys good parts, not processes. So, you can correlate pressure well, you can do all kinds of really neat things with processing, but if you don't get a good part with good appearance and good dimensions, it doesn't really matter. So the goal really is to get good parts, not necessarily a good process. I mean, typically a good process gives you a better chance at getting good parts, but ultimately it's the parts that matter. So the first thing you're going to do at the T1 tryout is you're going to run the phase 4 Moldflow process. This is essentially what's going to be reported out in the final report for Moldflow. Those process settings are going to be input into the molding machine with the help of the tool shop that's running it. And if those parts are not acceptable, the part supplier will then optimize the process at the T1 and forward the process back to the Moldflow source. So that's what 4A is all about. The guys that are running the machine there at the tool shop are going to dial it in the way they see fit after they run the initial process from the Moldflow analyst, and they're going to update that analysis and to the way they see fit. So those process settings are then going to be fed back to the Moldflow source, and that analysis will then be run from there. So it's kind of a bi-directional correlation, if you will. And then lastly, the phase 5 process is run, fully optimized, what's going to be run at the part supplier. So with that, there's a correlation scorecard that comes along with it. It documents the T1 tryout, documents dimensional and appearance responses, 3 sets of measurement, phase 4, phase 4A, and phase 5 that are forward and backward correlated. And this will be filled out both during and after the T1 tryout. This is kind of a quick look at it. And again, the details of all this would be something that would be the subject of an in-depth class and learning how to do this. Here's some worksheets. GM did a very good job and a very detailed job of putting together a spreadsheet to help the analyst and the part supplier fill this out at the press. Some more information here, some short shot pictures documented, a filled out example here. So you see the phase 4 stuff here from the Moldflow analysis, the actuals, and then this is what was developed by the process engineer at the tool shop. And then we have the dimensional correlation as well. And usually you take these points as a point of reference for measurement from the GD&T that was developed by GM, and you fill out the worksheet from there. So lastly, some advice here. Rely on experts. If this is something you haven't gone through before, we've attended dozens of these T1 trials, and we sit on the GM Moldflow advisory board, and we've given a lot of feedback to GM ourselves to help develop the standard. That's the spirit of Kaizen, is to do it, see what you like, see what you don't like. If there's something you don't like, you give that feedback and see what we can do to change it. So if you haven't gone through it before, rely on experts to help you through it. If you're not yet a Moldflow user, and you're considering having Moldflow in-house, and if you do, you certainly want to become expert certified, or you can use our services. I mean, it's a cheap sales pitch here, but we've been doing this for an awful long time, and we know what we're doing. Secondly, be prepared. Like I said, I've attended many T1 tryouts myself, and the ones that don't go so well are the ones for which people are not prepared. where there's been no discussion about what's going to happen at the press. You kind of get there and everybody's looking at each other, and then the process guy takes over and he does his own thing, and suddenly you have a big mess on your hands. So have a pre-T1 meeting. The mold shops and the part suppliers should all be aware of these standards to the extent that they know what they have to do and they know that it has to be done per GM's requirements. So have that meeting and discuss what's going to happen at the press so that when you get there, everybody's on the same page and you can get through it relatively quickly. If everything goes well, it really shouldn't take more than half a day to a day to get this done. And things happen at the press. I'm sure a lot of you have been at mold tryouts where the machine breaks or something in the mold's not working, but there really should be no excuse for if everything's working right. There should be no excuse not to get this done within a day. Work collaboratively. Lean on GM where you can. I mean, if you have questions about the standard or something's just not making sense to you, that's what they're there for. They're there to answer your questions. That's what the polymers group. They know the standard inside out, so you can lean on them or you can lean on us. If you just kind of go off as a renegade and try to do this all on your own, it can really sink a program. And all of those bad examples, and there are more that I haven't shown, can really cost a lot of time and money. And again, working collaboratively at the T1 tryout is extremely important to doing it efficiently and getting the most out of it. And be honest when things aren't working. I've seen suppliers out there try to fudge the data. It's not helpful. GM is not here to nail you when you get something wrong. They're there to get better parts. And when you're there to tell them exactly what's going on, then it works out well in the end. Sir Walter Scott said, "Oh, what a tangled web we weave when first we practice to deceive," and it will show up eventually if you try to trick things, so to speak. Bad news is way better early than late, and that's one of the reasons that GM has taken this on to do it very early in the design process anyway, so that when we find issues with manufacturing that we can identify early, we can incorporate them into the part design and not be surprised by it when we're ready to cut steel and everybody's in a rush stage. So that gives you the opportunity and the time to fix those problems. And then lastly, feedback to Autodesk makes things better for everyone. And there's a lot of things that are going on with Autodesk R&D right now that relate to some of the things that go on at the T1 tryout process. Appearance issues. There's a lot of things that Moldflow traditionally hasn't been able to identify as far as appearance is concerned. For example, tiger stripe. That's one of the things that Autodesk is working on. Secondly, having measuring dimensions as placed on a fixture, for example. So when you go to measure dimensions versus the GD&T, Moldflow is working on a way to try to allow us to measure things in Moldflow, in a constrained state on a fixture, for example, which currently we cannot do in the current version of Moldflow. So it's this feedback to Autodesk that eventually will improve the product to the point where we can start to identify all these things and fix them in a virtual world, so that when it gets to the manufacturing floor, it doesn't become a problem. So that's our advice for the day. So what's new at CAE Services? I mentioned the Autodesk partnership earlier. We are a reseller for Moldflow. We do provide training through the expert level. We are in the process of developing training for this very thing, the GM standards, the in-depth version of it for both the Moldflow side of it and the T1 tryout side of it. We have demo days for the software. If you ever have questions about Moldflow and you just want to spend an hour with CAE and just fire questions at us, that's what Moldflow Demo Days is about. On the learning side, we're building expert analysts, so we have training, classroom and online. We do have classroom training both in the Detroit area and here in the Chicago area where we're located. We have our webinars just like this. They're monthly topics, so check back to our webpage for future topics. The Moldflow office hours, actually, what I explained up here was more for Moldflow office hours. The demo days is to demo the software. The office hours is to just talk about any topic in Moldflow. And then, of course, you can find any of this on our website. So please visit our website to check out any webinar recordings we've done recently, including this one. And you can follow us on LinkedIn as well. So at this point, bear with me for a second. I did get some questions ahead of time that were asked. One of the questions was, is the Moldflow engineer required at the T1 tryout? And the short answer to that is yes. If the exact Moldflow engineer that actually worked on the project isn't available, you should definitely try to have somebody there, a representative from your company, because obviously you're trying to match what you've done in Moldflow at the press. So any questions that come up about the process and how that was reported out need to be answered by the Moldflow engineer, and make sure that you're not just taking the as gospel what the process engineer says as we definitely match that. So you need to see it with your eyes. I've gone to many mold tryouts where I've asked to see the process setup sheet ahead of time. They send it to me, and then I go to the tryout and it's something completely different. So you need to see with your eyes at the press what's shows up on the controller, so that you can be assured that what they're running matches what you ran in Moldflow. Another question, what is the best practice for comparison of simulation to the part results? So obviously, comparing simulation to part, you have to match the process as well as you can. And also, I mentioned earlier the material characterization is very important. So there are best practices for comparing them, and like I said, we're developing some training for that. Things like melt temperature and making sure we have the pressure, set up the same way as we do in Moldflow. Making sure we have the right fill speeds set up. One of the things that we do a lot on a lot of GM parts is use valve gate sequencing, for example. And you really have to do visual confirmation, for example, that the flow front actually reaches the nozzle tip. And if it's off just by a fraction, like maybe you see you've set it up by position or time, but the flow front doesn't get all the way back to the nozzle, then it's going to cause some hesitations and accelerations in the flow that give you a completely different filling pattern. So valve gate sequencing setup is extremely important to do in person and get visual confirmation on. So there's a lot of things like that go into making sure that the simulation and the molded parts match better. As far as another question here is how many iterations does GM require? Well, there was a chart that I showed earlier that actually answers that question. It's going to take a while to get back to that, but essentially just do as many as you can. That's the short answer. Each time, I think it's 10 iterations for each level of Moldflow, MF0, MF1, and MF2. And if it's a glass fiber filled material, for example, that goes up to 20. But anytime you're changing the mesh, that is considered an iteration in GM's book. And changing the mesh usually means changing the part design. So the expectation really is do as much as you can with the part design to affect the change. Another question is, I know Moldflow can simulate the warpage of a part, but are you able to use the warp analysis to actually cut the steel to it? And I think this is referring to windage. So the short answer is yes. And it used to be, we've done windage analysis for a long time, but the real trick with that was, how do we morph the part? We usually put that on the mold maker's plate we give them the right shape, but now they got to make it moldable so that there's no undercuts, things like that. But now we have that capability in-house. And, it really requires a tooling engineer to understand what the implications are of morphing this part. So the short answer is yes, we can simulate windage, we can morph parts, and there's a very efficient way to do it. Last question is, how can we trust Moldflow warpage results? Well, again, I'll just keep reiterating. Have an expert analyst. Make sure they understand tooling, make sure they understand processing, make sure they've got some experience at the press, so that the types of things that they're recommending make sense in all of those arenas. Make sure you have a very well characterized material, fully characterized, et cetera, et cetera. So all of those things go into getting the best possible analysis correlated back to the actual parts. Also looking at some questions online. Could one get the GM documents even when currently not working for GM? Yes, ihs.com. What kind of focus is GM putting into material characterization, i.e. putting pressure on material supplier to properly and fully characterize the material? They've been putting pressure on the material suppliers for a long time to do this, and GM put their money where their mouth is. They a long time ago put a lot of money for it to get a bank of materials tested, and they offer those material decks to all the expert certified and GM certified analysts when they're working on GM parts. So they've met with material suppliers, they've talked to them, and of course they expect material suppliers to provide material characterization as much as possible. Next question is, are the different groups within GM working together to understand the potential for additional mold construction costs, i.e. requiring conformal cooling, requiring specialty steels, etc.? I'm gonna open this one up to Darren. Let me unmute Darren here.
Can you hear me?
Yep.
Okay, thanks, Tim. So yeah, in GM, we do internally recognize that sometimes when we do conformal cooling or need to work on some sort of a part design issue, that it's going to affect the cost of the tool. So we do have some methods internally that we can, if we identify those items early enough in the process, we can get those costs captured in upfront budgets, as well as when we get into sourcing and tool cost reconciliation later. So those we do have avenues to capture those costs cross-functionally.
Okay, thanks, Darren. Next question. This one's probably I answered this a little bit earlier, but what is the GM expectation for correlation with molded parts, which would be measured on a fixture, free state or fixtured? Does GM have a recommended and reliable method of free state measurement if required? So basically, as I mentioned, Autodesk is working on having an analysis where we can constrain the part as if it were on a fixture. That is not currently available. It's being worked on. But currently Moldflow can only give you free state outputs, and that's the real disconnect. Is typically when you're measuring for GD&T, how well you're correlating with Moldflow results, you've got apples and oranges there. So the only way to really measure the correlation is to do free state, and really the best way to do free state is to do a laser scan. So if you've got laser scanning capabilities, I highly recommend you use them. You can overlay those results with predicted Moldflow results. So we've used that ourselves, and that seems to work pretty well. I mean, and you can do some things in CMM, take certain points, and the real key there is to make sure that the part is not so flimsy, where the gravity effect comes into play. In some parts like fascias, for example, I mean, it just is what it is. You can't measure a part that bends so much that it's no longer comparable to the Moldflow analysis. So, and that's one of the reasons that Autodesk is looking at doing things on a fixture, because that's a known thing. Free state, gravity takes effect sometimes. But if you have a more rigid part, and you can use the a CMM machine to take points, that's a perfectly valid way to do it as well. Just time for a couple more here. Can you explain the juncture loss difference? Okay, so juncture loss is, if you've ever taken a class in fluid mechanics, if you try to move a liquid or a fluid from point A to point B down a pipe, there's a pressure drop that's required to get it to move. Okay. When that pipe diameter changes, just to get across that barrier from diameter A to diameter B, and essentially move no distance across that barrier, there is another pressure loss or head loss that's involved, and that's what juncture loss is really taking care of. Okay, so a long time ago, Moldflow didn't used to test for that juncture loss, and when you model a runner system in Moldflow, you're using what are called beam elements, and those beam elements are the only thing that juncture loss relates to. Okay, so those juncture loss coefficients relate to pressure drops moving from point A to point B, across, from diameter A to diameter B, essentially going no distance. And of course, in a runner design, especially in manifold systems where you've got valve stems and all kinds of diameter changes, that can really change. That can really add a lot to the pressure requirement. So if juncture loss data is not available, you have to really pay attention to the fact that you may be predicting something that may not be molded at the press because you didn't account for that. So that's juncture loss in a nutshell. Last question here. Does GM require pressure-dependent viscosity in the material databases that it uses? So that's not something I covered here, but Darren, maybe you can correct me here. I don't think it's required, but it may be suggested. Pressure-dependent viscosity, before you answer that, Darren, I just want to explain what that is. When you have two things involved, typically, usually it's an amorphous material, particularly sensitive in a material like PC or PCABS. When your pressures start to get high, and we'll say high is something around 14, 15,000 PSI, the viscosity of the material starts to be a function of the pressure that's being applied to it. So the viscosity changes because the pressure is getting high. So that's not typical in a lot of materials, but those types of situations, pressure dependent viscosity can be influential. But Darren, maybe you can answer. I can't remember if it's actually required. I don't think it is.
We do require extensional viscosity, but not pressure dependent at the moment. But it is something that is on our radar. We may be updating it. Whenever we do testing internally, we do require that piece of it. So any of our internal material database files will have that value.
Okay. Yeah, I know there is some discussion. There are some material suppliers out there that maybe disagree a little bit with the pressure dependent viscosity and the way Moldflow does it. I won't mention names currently, but there is some debate about it out there. So just be aware of that. Okay, well, I think that covers a pretty good breadth of questions here. Like I said, this webinar is recorded and it will be on our website probably within the next day or two. So feel free to check back on that and look for our upcoming webinars. Lastly, I want to say thanks to Darren. I've known Darren for many years and worked with him, and you know, they've laid out a very good process here, and it's important. It's important not just to GM, it's important to the plastics industry to have standards. It's important to American manufacturing down the line. So standards really matter in terms of making things more efficient, making things better quality, and so forth. So so learn the standards. If you ever need any help, I'm available at any time to answer any questions. So so I appreciate you taking the time out of your day to attend, and hope to hear from you soon. Thanks, everybody.